All right, guys. I'm ready. This is like 1, 2. So I finished grading, but I need to post the solution so you can see, like, I mark kind of like what -1, -2. Okay, so I can show you like how the solutions look like. I have to just like activate that link, but the way you want to check is so you'll obviously see what I did, but then there's like a +2, +2. Those are like saying like, oh, if you got to here, it's +2, and then if you got up to here, it's another +2. And then all those numbers added together end up equaling 37. So like if you got like -5 points, then that means that you got 32 out of 37. So make sure that's calculated correctly. And then if it's obvious that I marked something that you got right, wrong, then you can or no. Yeah, if you found that I marked something wrong that you shouldn't have gotten, then you can let me know just by cross-referencing and checking against my solutions. Sometimes I might be really tired and give you credit for something that you actually did wrong. You don't have to tell me that unless you want to be honest. Yes.
Is there a curve or is this just the base grade?
It was no curve. It was just like I have a -1 or -2 for each little thing that you got wrong, and then I computed total score out of 37. And I guess the class average and median were kind of the same, but it was like an 85 or 83 or 5 or something like that. So it's pretty good. But so now you know how the tests are like. So you can see that generally they shouldn't be like pretty predictable, I think. Like it's like kind of similar to what you've been doing and stuff, but it is comprehensive. So like that's kind of my style, is that like I tend to ask one type of every little thing that you've seen. So one integrating factor, one separation variable, one method of interpolation, superposition, thermal cooling, mixture. So it was like it was comprehensive, but it's not like something like it's not like unpredictable, like like these things. And also like some people came to like office hours the week of the test or before the test, and I believe that could be pretty helpful because like I just give you problems that are really similar to the test. So so don't worry if the first test I mean, generally some people did really, really well, but and for those who did really well, like don't get complacent. But if you didn't do as well, doesn't mean that this is like gonna be what you end up in the class. So you can still do really well because I look at sort of how you improve through the semester. And the first test is just the first test. It's just whatever, and there's still like second and third, and then the final, and the final is weighted more. And if you like improve throughout the semester, I take that into account as well. And so just it's fine, don't worry, but just make sure you learn from this, and also like how it's like, and so now it helps. And maybe strategize on how you create your formula sheet. Like sometimes um you might think that you just do screenshots of a bunch of like examples and cram it all in, but sometimes it's good to like sort of have a study sheet that is sort of a little bit more digested or processed, and so you have like something that looks but so yeah, so you can reach out if you have any questions about that. But I'll also post the test solutions. I just had to just finish grading you guys, and then my other class, my calculus class, has a test today. So I started writing their test after I posted your grades, and you probably noticed that it was like already past midnight. So I just am kind of tired. So last time, we're gonna try to finish hopefully as much as we can this second order with non-homogeneous. So you have like a non-zero on the right hand side, but there are all these cases. So we looked at polynomial, we looked at exponential, and we looked at like a polynomial times exponential. And then for all of these, a good process is to compute the homogeneous solution first, because if you notice anything that conflicts with the like matches with the homogeneous solution, so your particular solution form, like in this case, there wasn't any because the way you do the particular solution is you look at the right-hand side. That gives you the first form. This one's t times e to the negative t, and I hopefully convinced you that the right form for this would be a general first degree polynomial times the same exponential that you see here. And you can't go lower than 1 degree in this case, because then you'll have no t terms on the left-hand side that match with this t term on the right-hand side. And you could go higher, but it's not necessary because there's going to be a bunch of t squared terms on the left that are going to have a coefficient that's equal to 0 anyways. But this has e to the negative t, whereas the homogeneous solution, both of them is just e to the t and e to the negative 2t. And those exponentials don't match, so there are no terms that match between these two. So we don't have to multiply by t. But the fact that your particular solution is a first degree polynomial times an exponential means that you have to do the product rule. And I spared you from watching me actually do all of it in detail, but this is the final result if you took the derivative and the second derivative and then plugged everything in. And then you'll get a naught and a1 is equal to 1/4 and negative half. And so this is where it's important because this t right here looks like it's just a t. So you might think, oh, my particular solution will just be a times t times e to the negative t. But you do need a general first degree polynomial. You need this a naught and this a1t because this a naught actually wasn't 0. It was some other number here. So you'll have an issue if you try to plug in a non-general first degree polynomial. Just because you saw this t, you do also need the a naught plus the a1t. And then there are times where, like, in this case, I probably just switched the right-hand side. So it used to be e to the negative t, but I made it e to the positive t. This was on purpose because I knew the left-hand side would have the same homogeneous solution. But if I just change the right-hand side to this, our initial particular solution form will have this exponential instead, which I know is going to conflict with the first homogeneous solution. And if you had plugged this in, you're going to have some kind of issue where you get a false statement, and you're not able to find your coefficients a0 and a1. And so the solution, which we'll see why later, is to multiply the whole thing by t. And the whole thing by t. So you'll have like t here, and then this one's already got a t, so it'll be a t squared. And then, of course, it's a pain to find these derivatives. But if you check on your own, you'll hopefully find that these are the right derivatives. And then you plug those in. In this case, we have two unknowns, because there's this a naught and a1. But there end up being three matching conditions. So the purple equation, the orange, and the red. But so one of them is extraneous because you only need two equations for two unknowns. So the purple ends up giving you something not useful, although it's true, 0 does equal 0. The other two end up working out to give you your a naught and a1s, and then that's your general solution. So that's was kind of painful last time because it looked like there was a lot of algebra and work, but I don't, yeah, hopefully the homework, I don't think the homework is going to be as long. But it's good to do something maybe harder in class, and then you don't have that to work on. So this is still, we're looking at an exponential. What did I do that's different between this and this? So I always do some modifications to it. So you got the t e to the t, t e to the t. So it looks like the only thing I did was change the left-hand side. This right-hand side are the same. But let's see what happens if you end up changing like this left-hand side to this right here. That's the only change I made. And it's like nice to see like these changes and what kind of effect that would have in the solution. Of course, this right here is going to require us to build a new characteristic equation. So it's going to be r squared minus 2r plus 1 is equal to 0. And then this factors to, it's just r minus 1 all squared equals 0. So this is going to end up being r is equal to 2. But of course, it's a double root because you see this 2 here. So that causes it to be a double root. And we know for a double root, homogeneous, yes. Oh, sorry, r equals 1. What am I doing? Uh, so you can tell that I'm very tired today. So it's R equals 1. And so therefore, our homogeneous solution is going to be, one of them is C1 e to the 1 times t, and the other one is C2 t e to the t again. And so that's our homogeneous solution. And we already know from before that the right-hand side is the same as before we had. So it's going to be x of p is equal to a general first-degree polynomial, a naught plus a1t times this exponential et. And if you multiply this out, you get a1t e to the t. And there's literally no way that this is gonna satisfy this non-homogeneous equation because it matches exactly, it looks exactly like the homogeneous solution, right? C1 e to the t. Okay, so C1's any arbitrary. So for any arbitrary C1 and for any arbitrary C2, this will satisfy the differential equation with a 0 on the right-hand side. So this one right here, A naught and A1 is not necessarily arbitrary. We're attempting to try to find A naught and A1. What that will force us to be able to satisfy this non-homogeneous equation, right? But if any arbitrary constants multiplied to these are going to not work, then there's no hope that we're going to find an A naught and A1 that will actually satisfy this equation with a non-zero. What you're going to get if you try to plug this in, I can tell you right away, you'll get 0 is equal to t e to the t. Again, that's a false statement, something similar to what we've seen before. So there's really no hope that this thing will satisfy. Of course, you got these are the same, and then these are the same. So what you're going to do is you're going to multiply by t, the whole thing. And if you do that, you'll end up getting a naught. And then I'll make it clear that like this used to not have a t, that t is going to be here. And then we're going to have e to the t plus, and then we'll have the a1. And then this was used to be a t, but I'll put a squared on this to signify that that's the additional t that ended up getting multiplied, and then e to the t. Yes.
So it's okay if one of them matches the homogeneous solution, but just both can't.
It's also not good for one of them to match. So here, if one of them matches, and you know, actually we saw this way back as well. Let's see here. Where is it? I think I remember. So we had this one was a second order equation with a t. So t is a 1 degree polynomial. So you'd assume that this is a similar case with first order equations, that the particular solution form will be a general first degree polynomial, a naught plus a1t. And we actually plugged this in and we got like, okay, the derivative, second derivative, x double prime, okay, the derivative x prime is just a1. That's the a1 here. And then if I took the derivative of that, that's 0. So you get 0 plus a1 is equal to t, which is equal to a naught, a1 is equal to t. But this was like, so a1 was we assumed was a constant going to this. So like we would have not gotten x prime is a1 and x double prime is 0 had we not assumed that a naught and a1 were constants. So we're like contradicting ourselves when we're saying, okay, well now a1 is equal to t. And then I might have taken it off, but like if you actually like plug this in to the differential equation, first of all, you have no way of knowing what a naught is. So a naught you might just leave. But then if you plugged in a t for a1, then you actually don't get this to satisfy this differential equation. So the reason this was an issue, we ended up multiplying it by t. So the correct solution form was to multiply everything by t. But you could have been able to tell that this would have given you some issue because one of the terms matched with the homogeneous. So if you did the characteristic equation, you get C1 plus C2 e to the negative t. E to the negative t is not an issue, but the C1 and this constant term here, they match. So it's not like the entire particular solution matched, it was just one of the terms that match. This usually leads to a contradiction, like where you assuming that they're constants, and then you get like that one of them is not a constant, and sometimes the other one you can't even find because this one A naught just disappeared from everything, and there was like, what is A naught at that point? If the entire particular solution, all the terms match with the homogeneous, then you'll get a false statement, like a 0 equals something that's not 0. So if one of them matches, you'll probably get a contradiction where it looks like one of the coefficients has to be a non-constant, even though you went into it thinking it's a constant or assuming it's a constant. And then if the entire thing matches, then it's going to give you a false statement. So those are two issues that we don't want to have. And the fix has been to multiply it by t, which you're just gonna have to take for granted for now. And I mean, you could at least be happy to know that if you do that, we always don't get an issue, so we don't get a contradiction. Like we always get like they're constants, and we also don't get a false statement. So you might be like, well, I feel justified that this is correct by virtue of the fact that it works. But if you're not satisfied with that, then you can wait later, and we'll talk about like other methods that would more systematically show these are some things that have to happen. So this one does this still have issues?
Yeah.
Yes, because now this one doesn't match, but this one does. So this, if you plugged in, will give you a straight up false statement because 0 equals t to the t. This one will likely give you a contradiction for one of the coefficients. So we'll have to multiply by t again. So if you multiply by t again, then the changes that are going to happen is you'll have a naught. This orange t is now going to become a t squared, e to the t, plus a1. This t cubed squared is now going to be a t to the cubed. And then it's going to be e to the t. And so in the end, it's as if you multiplied by t twice. So some people, they just say, well, we could have just, noticed that there were two terms that conflicted. So maybe you might just say, well, why don't I just like go directly and just say multiply by t twice? You don't have to do it one at a time if you already know that it's going to probably need it twice. Um, then it's going to look like it's just going to equal t squared times basically the a naught plus a1t e to the t. So it's just like this original thing that without having it being multiplied out. But if it's easier for you to visualize, like if terms will match, then yeah, you can multiply it out. But at the end of the day, it's like we just multiplied by t twice anyways. And so that's your correct solution form for XP. This now has no terms that conflict or match with your homogeneous. So if you plug it in, you won't get a false statement, you won't get a contradiction. So this is the correct solution form, the correct XP form. And this would be a huge pain if you were to try to actually solve for it. Although it's just two coefficients, a naught and a1, to plug it in requires doing like a three-way product rule because there's a t squared here. I guess you can multiply it out and then just do, but there's obviously like a product rule of some sort here that's going to become a pain. In addition to just taking a derivative, you have to take a second derivative, which is a lot of work. So that's why make sure you read or anytime it looks like going to be a gigantic mess, if it says find the correct solution form to the particular solution form, they mean this. They mean like just leave it without actually solving for a naught and a1. That's just asking you for the form, the correct form. And so that's the answer for that one. Okay, so we did polynomial, we did exponential, we did polynomial times exponential. The other case is a sinusoidal forcing. So if you had like sine or cosine, this is a sinusoidal forcing. And the kind of particular solution you'd expect is similar, it's the same as the one you had for first order equation. Why does this make sense? Is because if you plug this into this differential equation on the left, all the cosines and sine terms their derivatives will basically be also cosines and sines. They just like basically a sine turns into cosine and cosine turns into negative sine. And so you'll have a bunch of sines and cosines on the left, and you just want to make sure that all the cosine terms end up equaling to 0. So you'll try to find all the coefficients A and B that would make that happen. And then all the sine terms that pop out on the left have to equal sine of 2t. And we saw back then that, although it looks like it's just sine, well, it is just sine of 2t on the right-hand side here. And you might think naively that your particular solution, you might think you don't need this one. Like you could just like do without this and just have this. But that generally ends up causing you to have a situation where you'll be like, B has to be this and this at the same time. Remember that? Like where it's like B had to be equal to this. There was like a dilemma that occurs. So you needed this extra degree of freedom by introducing another term like a cosine of that kind of thing. So you could go back and see that how is the same with the first order equations. So that's why we needed both of these. Now, what's new about this is, so we're going to say this is our particular solution form that we build from looking at the right-hand side. But that that's just the starting particular solution. You might have to do like something to it, which is like multiply by t. And you may have to multiply by t like more than once, but you're just going to have to find a homogeneous solution to be able to tell if that's going to be what you'll need to do. So you have r is equal to, this is going to give you r squared is equal to -4. And then, of course, this is like saying r is equal to plus or minus square root of -4, which is like plus or minus 2i. And this was one of those cases we had for homogeneous complex roots. And to write the real solution to this, we'll just have to go back up. I'm going to just grab this, right? This was so this was saying like if you have a homogeneous equation, second order with 0 on the right-hand side, the solution, if you get a complex root, the roots would occur in conjugate pairs. You read off the real part and the imaginary part, and those go into here. And this is like what you would write on your formula sheet. We derive this using Euler's formula, but you don't have to derive it ever again. So that's the expression that you'll use. And so the only thing you'll have to look at is this right here. What's alpha? Yeah, it's 0. And then what's beta? Yeah, so there is this pure imaginary. Being pure imaginary, there's no real part, so that's 0. So then your homogeneous solution is going to equal C1 e to the 0t because alpha is 0. And because alpha is 0 and e raised to 0 is 1, this is just going to be 1. So I'll just not write anything. Cosine of 2t because beta is 2. And same idea with this right here. C2 e to the 0 is 1. So sine of 2t. This is your homogeneous solution, the real homogeneous solution. And I guess I also point out that like just this probably is pretty self-explanatory, but of course the kind of trig function you use is the same trig function, so that has to have the same argument. You need the 2t because obviously if you're trying to plug this into the left-hand side, you'll need x double prime and x prime potentially to pop out cosine of 2t and sine of 2t. If you forgot to say 2t for this, then you'll just have a bunch of cosine t and sine t's on the left. There's no way that's going to match with sine of 2t on the right. So the other thing we need to, of course, that's what we think for the particular solution is going to be. Like, so I'll just zoom out a little bit and then say, okay, this is our homogeneous solution. But looking at the right-hand side, right, our particular solution, like we wrote here, is a cosine of 2t plus b sine of 2t. but there is a problem because what does it look like? It looks like the entirety of the particular solution, right, matches with the form of the homogeneous solution. So it's like this is saying for any C2 and C1 and C2, this will satisfy this differential equation with the 0 on the right-hand side. But our particular solution, as it looks now, resembles exactly every part of the homogeneous solution. So we're even if we attempt to find a capital A and capital B, that would force us to satisfy this differential equation with a non-zero right-hand side, it's going to be impossible because for any arbitrary C1 and C2, these coefficients, this is not going to satisfy this. It's going to satisfy with a 0 on the right-hand side. So this is a classic case where you'll get like a false statement. You get 0 is equal to sine of 2t if you attempted to do this. So the solution is to multiply by t, because obviously the entire thing is matching. So this matches with this. This matches with this. So we're going to multiply by t. So if you multiply by t, then you get x of p is equal to just t times all of it's multiplied by t. So there's just this additional, I'll maybe use color. So then this will be orange. So this t got multiplied. This time you don't, even though it looks like two terms got, two terms matched. And last time when that happened, it was like multiplying by t twice. But this one, you only need it to multiply by t once, because if you look at this, the t distributes to each of these, and there's no issue now because these don't have t's, and each of these two will have t's. And so this is your correct solution form. So this is your correct xp. And I guess this time I'm asking you to find the answer to this. So that means that x double prime 4x. So, okay, what we'll do is we'll actually try to solve this. The hardest part is to take the derivative of this, which requires the product rule. And so it's a cosine of 2t, b sine of 2t. T negative 2a sine of 2t. That's the first derivative. Yeah, I mean, you'll just have to check these if you're curious to see if these are correct. Later, the second derivative is going to be more work because there's more terms to take the derivative. That's probably cosine. And then both negatives. So it's just calculus, but you'll just have to, yeah, you just have to do the product rule, and then you'll get these, which is a pain. But if you do that, then you'll get these, and then you're just gonna plug it in. So plug this in. So we got x double prime, which is all of this. So I'll just copy this down. And then you have plus 4 times x. There's no x prime in this left-hand side. So it's just the x. So it's just this one. And this is not, it's too big, so I'll just shrink it a little bit. this has to equal sine of 2t. All right, so now we just have to like consolidate all the sine and cosine terms on the left-hand side, and then all the cosine terms have to vanish. But what I'll point out here is that if you look at this term right here, this, if you distribute the 4 out, or I guess we can even distribute a negative 4 out, it would be negative 4t times a cosine of 2t plus b sine of 2t, right? And if you look at that, this is plus 4t a cosine of 2t plus b sine of 2t. This is minus 4t a cosine of 2t, blah, blah, blah. So it's clear that these two really are just going to cancel each other. Okay. And so we're only left with this one after. So you have just distributing it out, it'll be negative 4 times, I mean, maybe it was really hard to see if it's purple, so I'll just like make it all black, I guess. Black. But I'll make these still green. So you can see that this, after you distribute, is negative 4 all this. This is positive 4 all that, so they're going to cancel. So you got this one is negative 4a sine of 2t. Then you distribute this, it'll be plus 4b cosine of 2t is equal to sine of 2t. And this is like your classic, I've got sine term here and a sine term here. They have to match. And you also want this one to go away. And immediately we know if there's no cosine on this side, for this to go away, we need b is equal to 0. That's immediate. Well, the other one's also pretty immediate too, because you just have that negative, whoops, I'll use orange. You've got negative 4a has to equal 1, right? Which means that a has to equal negative 1/4. And so we got this. And then we just go all the way back to this was our particular solution, right? This was the particular solution. Not the original, it was multiplied by t. So this was the one we ended up using, and this was the one that will not give us a false statement. This is a case where you would have gotten a 0 equals sine of 2t false statement if you tried to plug in the original version. But this version is the correct one, and it works successfully. And turns out that multiplying by t magically fixes all the problems that you would have had. And not only do you not get a false statement, you also get constants for a and b, as you would expect, or you assumed going in. And so this is our solution form, but you're going to have a is equal to what, negative 1/4? And b is equal to 0. And so your full general solution will end up being, it'll just be like this goes away, right? Because b 0, this is just going to distribute out to negative 1/4 t. I like putting the numbers in the front. A is equal to negative 1/4. That goes out, and then cosine of 2t. And that's your particular solution at the end of the day. And then you're just going to add to it your homogeneous solution. We must have computed that earlier. It's right here. This one. Delete all this. So that's your homogeneous solution. And those together, right, we're used to seeing that is going to be your general solution. The general solution contains both C1s and C2s. All second order equations will have 2 arbitrary constants. And in this case, the particular solution, it's just the t cosine of 2t term with a negative 1/4 in the front. So I guess it's a little, so I told you that like for you to not get any kind of dilemma or some kind of issue where like one of your coefficients has to be one and the other at the same time, you do need both cosine and sine, both of those, like I said. If you just said, oh, I just have a solution form that's because it looks like there's sine on the right-hand side, I'm just going to use the sine term and just do that. That's not going to work. And not only that, in this particular one, it was the cosine that actually stayed at the end, right? It wasn't even the sine that stayed. So we kept both. We kept cosine and sine. And you're thinking, well, maybe I don't even need the cosine because the right-hand side is sine. But you do want to put both. And in this case, it turned out that the b went to 0, and it was the cosine that stayed. So it's clear from that that you probably want both because you don't even know which one's going to stay later. I mean, we kind of did, yes. Well, there's going to be a more complicated in a moment, and we'll maybe get there. But see, this is what happens eventually. Is like it might be a polynomial and things.
The A variable.
Okay. Well, you could use the letters are not important. So you could use like whatever letter you want. You could use B for the cosine, A for the sine. You could use, X. You could use whatever. I mean, you don't want to maybe use X, that's the solution, but like you could use Q and P and anything. Those are just arbitrary letters. You could even use Greek letters or whatever. So let's just really hammer down like why you need, and most people, I mean, pretty much everyone didn't have that issue because in the test we had a sinusoidal forcing for the Newton's law of cooling problem, and I had a sine term or something there, and everybody who did do the method of undetermined coefficients for that problem did actually build the particular solution correctly by having both the cosine and sine terms. But let's suppose hypothetically you didn't do that and you said, oh, it's just going to be a sine of t. Because you look at the right-hand side and you're like, I'm not going to add the cosine term. Well, then your xp prime would end up being a cosine of t, because that's the derivative. And then your xp double prime will end up being negative a sine of t, because the derivative of cosine is negative sine. And let's suppose you had just assume that you could just get away with just the sine and not have the other cosine term. Then if you plug it in, you already computed everything here. So 2, it'll be 2 negative a, because this is the second derivative, sine of t. And then the derivative term would be plus a cosine of t. That's the x prime term, because this is 1. Plus the actual x is going to be this. And we're trying to find, like, this is our solution form. We're trying to force this to satisfy this differential equation. It only has one undetermined coefficient, capital A. So we're trying to find that capital A that will force this thing to satisfy this differential equation with sine of t on the right-hand side. And so if you try to do this, the classic approach is you're just going to combine all your sine terms and all your cosine terms and then do matching on each side. So if you look on this side, you have minus 2a sine of t, but plus a sine of t. So it's going to be negative a sine of t plus a capital A cosine of t equals sine of t. But there's a problem here because now you're just saying I need this to match with this, but simultaneously I need this to disappear. So the fact that you want this to disappear means that capital A has to equal 0. While you also want this to have this thing, right? You want negative a to equal 1, which means that a has to equal negative 1. And so, like, you'll have this issue that shows up where you have two things that a has to be. So you cannot find a that works. Because you can't, say a is 0 and negative 1 at the same time. This is a classic situation where you do not have enough degrees of freedom to get this solution to satisfy this differential equation. Therefore, we needed to add another term. And so in this case, we needed our solution to be like a cosine of t plus b sine of t. You needed both of these. And I could use a of sine of t plus a v of cosine of t. Those are the letters are not as important, but this you needed to have because if you didn't, then you're need both trig terms in your this will give you enough degrees of freedom to be able to force. So this is incorrect. Wrong solution form. I think I did something similar when we did first order equations. So the same idea for second order equations. You'll get this issue if you didn't use the full that one. So that's so you have all these cases. So that one you just did was just this a sinusoidal function on its own. But if you had a product of, in this case, a degree 1 polynomial, and a sinusoidal. Um, your particular solution, you want to use this, but let me motivate why this makes sense. You want to be able to have a particular solution that if you plug into the left-hand side, will give you a bunch of terms that resemble the right-hand side. And so if I were to take the derivative of this thing, there's a product rule. The product rule will mean that in some instances, I'll take the derivative of the first and then keep the second. And in other instances, I'll take the derivative of the second and keep the first. And every time I take the derivative of each of these sine and cosines, they just flip to the other one. I mean, like, sine goes to cosine and cosine becomes sine up to some sine. Every time I take a derivative of these polynomials, they just go down by 1 degree. So they currently has a t term in there that'll just go away and you'll just have constant, right? So it goes from a linear to a constant. And if it was a quadratic, then quadratic to a linear to a constant. Anytime you take a derivative, you shed a degree. And so like intuitively or immorally, what's happening on the right-hand side is you're going to have a bunch of either linear polynomials multiplied with trig functions or constants multiplied with trig functions, which is fine because what we have on the right-hand side is a linear t multiplied with a sine. And so you'll have like, a bunch of linear polynomials times cosine and sines, and you just want to make sure that you find a naught, a1, and b naught, and b1 that'll eliminate everything except for all the t sine of t's. And then you'll have a bunch of constants times trig functions on the right-hand side, on the left-hand side, and you want also those to vanish. But you have things that are going to resemble, on the t to the sine of t on the right, and that's good. What we don't want is something like this. So like I'll write up here, like what we had before was just a cosine of t plus b sine of t. This is not going to be enough because if I plug this into the left-hand side, you're never going to have anything that has a t times a trig function, right? There's no hope of, anytime you take a derivative of this, it's not going to pop out a t. It's not, right? So there's no hope that this thing will, if you plug it into the left-hand side, give you terms that have a t times a sine of t, so we needed this. You could have like an additional like a2 t to the squared and a b2 t to the squared, but that's not necessary. That'll end up popping out terms on the left that have t squareds times trig functions, but there are no t squareds times trig functions. And so all of those will have an a2 or b2 on it, and those a2 and b2s will just be 0. So you don't have to do that. So this makes sense just from that standpoint. And so we'll just say we need that. It turns out you also need to have a general first degree polynomial. So you can't just get away with like, you can't omit a naught and b naught. You need, just because you see this t, you need it to be a general first degree polynomial. So it's like a naught plus a1t, b naught plus b1t. And just like before, where you can't assume that a and b are the same, right? They're not necessarily the same up here. In this case, we're going to assume that the general first degree polynomial that multiplies the cosine and the general first degree polynomial that multiplies the sine are not necessarily going to be the same. They may happen to be the same, but you don't assume that ahead of time. So if you end up getting a naught is also equal, like you get a naught is equal to 2 and you get b naught is equal to 2, maybe that may happen, but you don't, that may not necessarily happen either. So you don't assume things ahead of time. You just keep things as general as possible. If things fall out to, some things might equal, like A1 might equal B1, well, maybe yeah, it might happen, but it may not. So you don't know that it would, so you're not going to assume that ahead of time. If it turns out that it does, that's fine. So you have that. And so for this one, I guess the what is it? It's just the same left-hand side as this, so I'll just copy and paste this, and then that's all I can probably do. So it's probably just going to be this is your homogeneous solution for this one, because it's x double prime plus 4x, x double prime plus 4x. So this is the same homogeneous solution that we got before, but I'm going to just delete the rest of this because we're going to have a different particular solution, but at least we'll have this to start with. So the process is still the same. You're just going to find the homogeneous solution. This turned out to be r squared plus 4 like we had before, and this is all this. Then we're going to use this, and then we're just going to probably just see if we need to multiply by t or not, depending on if there's any matching. So yeah, I'll see you guys later on Friday, or I have office hours today too, so.